So welcome back and good morning. And today we'll see the temperature rise time curves. That is, mainly we'll see heating time curve as well as cooling time curve of any electrical machine. See, in the previous material that I have shared with you, you might have read about various enclosures. Enclosures in the sense how much ventilation is provided. So ventilations, they are actually a way for heat transfer or heat dissipation. Heat transfer in the sense the inside temperature or the inside heat energy is dissipated to the surroundings or to some other cooling medium. So these are all very significant in the sense that if proper heat dissipation is not envisaged in a machine, then so the certain parts are very vulnerable to temperature rise. So they will become hot spots, and at that point, insulation failure will act, and finally, it affects the life of the machine, or it will end up in a short circuit where you have to again rewind the machine. So the rewinding of the machine will reduce the efficiency. Okay, so heating is very important as well as cooling is also important. So we have to identify what is a pattern of heating. Okay, that is what is the rise time of temperature or what is the final steady state temperature. Okay, and as t tends to infinity, at what temperature it will become constant. Okay, anyway temperature will rise and it may reach a constant point. Okay, will it reach a constant point? If it reaches, what is that constant temperature? Okay, likewise, how much time it takes for cooling. Okay, cooling can be of mainly of two types. That is, if the machine is shut down for a very long time, it will be cooling, and the final temperature may be 0 degrees Celsius. But for most of the time, the machine will be operating close to full load condition. That means the temperature may increase or it may settle at some steady state value. But suppose if the machine is having some part load operation, if the load is having if the load is part time, that is part load, that is only semi load, only some portion of load is only there in the machine, then certain cooling is allowed. Then the machine may cool down. If in that sense, it may settle down to it will not come the temperature may not come down to 0 degrees Celsius, but in such cases the temperature decreases and settle down at some steady state temperature. Okay, of course there is cooling, but it will settle down to some uh, temperature. Okay, so all those things we'll see in these portions. And one more very important thing is that, see, when we see the heating and cooling curves, we may think that a machine is a homogeneous body. Homogeneous body in the sense every part of the machine is made of the same material, but that is not the case. We know that core is made of iron, then we have yoke, then we have insulation, then we have windings which are made of copper. So each and every part is made of different materials, or all these materials are having different thermal resistivities. Okay, so in that case you can never consider this as a homogeneous body, that is heating of one region is different from the other region. Okay, so uh, so we are actually, as we are considering this machine as a homogeneous body, and we are actually calculating the heating the cooling and the heating rise curves. See, so this is more or less effective, and we'll get an idea of overall, we'll get an idea as to how much the temperature increases, where will be the steady state temperature, or how much time it takes for cooling, and what is the final steady state temperature by cooling if there is a part load operation. Okay, so we are going to the derivation, only two simple derivations. We'll go to that. So before going to that, we have to learn certain uh, terms. So this is one term, that is Q. What is Q? Q is nothing but the power loss or heat developed. That is, the unit is in joules per second or watts. Then G, the weight of active parts. Okay, that is what is the active part? A winding may have two different parts, that is inactive part and the active part. Active part is a region which is coming in with the which actually takes part in the electromechanical conversion, energy conversion portion. Electromechanical conversion portion, that part is called the active portion. So weight of that part is G. Okay, kilogram. Then specific heat, we know what is specific heat, that is represented as more H, that is joules per kilogram degree Celsius. So what is specific heat? That is how much heat energy is required to raise the temperature of 1 kilogram of material by 1 degree Celsius. That is specific heat. So specific heat is an index of what? Energy storage. Energy storage. I repeat, energy storage. So then we have S, capital S, that is a cooling surface. So in meter square. And then we have specific heat dissipation. So what is specific heat dissipation? How much heat is dissipated? Heat energy is dissipated. Heat is dissipated from a from a 1 square meter of surface when there is a 1 degree rise in temperature. What is that 1 degree temperature rise? That is 1 degrees temperature rise over the ambient temperature. So when does the heat dissipate? Heat will dissipate only when the temperature of the machine is over the temperature of the ambient medium. So if it is over the ambient temperature of the ambient medium by 1 degree Celsius, how much heat is lost to the surroundings per meter square? That is actually specific heat dissipation. And we have the cooling coefficient, which is the inverse of lambda. And then we have theta, the temperature rise at any time t. And then we have the two temperatures, that is theta m while heating and theta n while cooling. So what is theta m? Theta m is the final steady state temperature rise while heating, and theta n is the final steady state temperature rise while cooling. That is during, as I mentioned in the previous just before, that is while cooling. For part load operation, it allows some cooling, so it will not settle down to 0 degrees Celsius, but the temperature will come down and it will settle down to a final temperature, that is actually theta n. If the machine is shut down for very long time, then theta n becomes 0. Okay, otherwise theta n will have a value. Okay, then theta is the initial temperature rise over the ambient medium, the initial temperature rise over the ambient medium, that is degree Celsius. And th is of course the heating time constant, and tc is the cooling time constant in seconds. Time is t is, of course, you know, it is time in seconds. Okay, now we'll see the first, the heating equation, that is see, first we have the overall heat energy is actually heat energy developed in a machine is actually having two parts. That is, one is the heat developed per second, or heat stored in the material, plus the heat dissipated. Two parts, heat stored plus heat dissipated. Okay, so first we'll see what is the amount of heat stored. So considering the conditions at any time t from the start, heat energy developed in the body during an infinitely small time dt. So what is the heat developed in the body during an infinitely small time dt? So what is that? That is power loss. Power loss, heat energy developed per second into dt. That is heat energy developed per second is nothing but what? Heat energy developed per second, that is joules per second, is nothing but q multiplied by dt. That's a time we are considering, that is t dt. So what happens? Joules per second multiplied by seconds, will seconds and seconds gets cancelled, that is joules. So this is the heat energy stored in that material. Okay, that is q dt, that is for a time, small time dt, this much is the heat energy stored. Okay, now if during this period dt the temperature of the body rises by d theta, the heat energy stored in the material, in the body, the heat energy stored, what is the heat energy stored? Weight of the body, weight of the body into specific heat into difference in temperature, that is total heat developed is q dt. So sorry, this is not the energy stored, this is the total heat developed, the power loss or heat developed in time dt is actually q multiplied by dt. And what is energy stored? This is the first component, that is weight of the body. Weight of the body is actually g. Specific heat, that is actually lambda. And difference in temperature, what is the difference in temperature? It is d theta. Okay, so what is a unit? G is having a unit kilogram, H is having a unit joules per kilogram degree Celsius, and the difference in temperature is actually in degree Celsius. So what happens? Kilogram and kilogram gets cancelled, degree Celsius and degree Celsius gets cancelled. Finally, we'll get an equation, a value in joules, that is the heat energy stored in the material. So we have the first part of the heat developed, that is gh d theta. Now we have to go for the next part, that is the heat dissipated. So when does the heat dissipate? Heat will dissipate only when there is a temperature rise over the temperature of the ambient medium. So when the temperature of the body rises above the ambient medium, heat will dissipate in any three modes, that is radiation, conduction and convection. So what is that? That is specific heat dissipation into surface, into temperature rise, into time. So specific heat is actually lambda. Surface, there is a cooling surface in meter square area, that is S. Now theta is the temperature over the rise over the ambient medium, and dt is the time that we are taking. Okay, so if we just look at this, that is specific heat dissipation will have a unit watts per meter square. Then cooling surface will have an area meter square. Then we have degrees Celsius for temperature and S4. So meter square and meter square gets cancelled. Watts is actually joules per second. Seconds and seconds gets cancelled. Again, we can see that heat energy dissipated is having a unit in joules. So this is the second part. This is the first part. Okay. So what is the total heat developed in the time dt? That is q dt, which is having the first part, that is the energy stored plus the energy dissipated. So from here you get the value dt. dt equal to d theta by q by gh minus s lambda by gh into theta. Solving this differential equation, so what we get? We get T equal to minus gh by s lambda log to the base e q by gh minus s lambda gh theta plus an integration constant k. Okay, now we have to find the k value, so we have to apply, we are totally applying two boundary conditions. First we apply the first boundary condition to find k. So what happens at the initial point, that is what is the case when we just start the machine? That is, we are starting the machine at a time t is equal to 0. So t is equal to 0 is a point where we start the machine. So when we start the machine, the initial temperature is nothing but theta I. Theta is equal to theta I. So time t is equal to 0, instead of theta we substitute theta I. So from here you get the value of k as gh s lambda log to the base eq by gh minus s lambda gh theta I. Okay, so if we substitute the value of k in that previous equation, this was the first part, this is what we replace for k. And if you take minus gh by s lambda outside, we'll get log to the base e q s lambda minus theta by q by s lambda minus theta I. Next we apply the next boundary condition. Initially we applied for t is equal to 0. Now the machine reaches a final steady state temperature rise theta m when t tends to infinity. Initially it was, the first boundary condition was for t is equal to 0. Now we have to see what happens when t tends to infinity. So when t tends to infinity, the machine will settle down to a final steady temperature rise theta m. Under this condition there is no temperature rise, and the rate of heat production. And why there is no temperature rise? When if it settled down to one temperature, we can tell that there is no temperature rise. So what is the reason for no temperature rise? The reason for that is that, see, whatever is the heat produced is being dissipated. That means there is no storage. The stored heat energy stored is 0. That is why there is no temperature rise. So if there is no temperature rise, whatever heat is produced is being dissipated. Okay, so heat production is equal to heat dissipated. So that means the change in temperature is d theta is equal to 0. And gh, so what is this? See, if we go to the that is this equation, if d theta is 0, then gh d theta is of course 0. That is, the heat developed is equal to the heat dissipated. Okay, now that means q d theta is nothing but the heat dissipated, that is s lambda. Instead of theta we have theta and dt. From here theta m is nothing but q by s lambda, or okay, 1 by lambda we can substitute it as z. Okay, no, there is no, that is what, then the theta m is q by s lambda. So if you substitute for theta m in this equation, where is it? Okay, so theta m is q by s lambda, and if you substitute for q by s lambda here by theta m, we'll get t is equal to minus gh by s lambda log to the base e theta m by minus theta by theta m minus theta I. Okay, now this part, that is gh by s lambda, is known as the heating time constant. Why is it called as a heating time constant? If you substitute all the units of these terms, then you can get that it is having a dimension of seconds. That is why this term is called a heating time constant. So if we substitute the value th for that, we'll get t is equal to minus th log to the base e theta m minus theta by theta m minus theta I. Okay, So rest of the portion, I'll just record another video immediately after this that will be continued in the next video. Thank you.